Good morning. We are going to study Unit 4, that is the second part of the solution of non-electrolytes. In this, we are going to study some non-ideal systems. In Unit 3, we have studied the equations and the systems showing ideal behavior following Rolle's law. But here we will see the systems which are showing either positive or negative deviation from the ideal behaviorality. And also we will study some azeotropic systems having maximum and a minimum boiling points. Then we will apply the equations on the colligative properties. These colligative properties you have already studied in 12th. But here we will consider the colligative properties with respect to the chemical potential. Then we will see the steam distillation processes. Now, by the end of this unit, you will be able to study all the colligative properties. You can perform the calculations using mathematical equations for calculating the molecular weight of the solute. Then you can describe the process of distillation and its practical utility. Then you can see the applications of all these colligative properties. Now, first of all, we will see what is ideal and non-ideal solution. Ideal solution we have studied in the unit 3rd, where we have successfully seen that delta H of mixing is 0 for ideal solution. That means for non-ideal solution it must not be 0. We have seen in unit 3rd that volume of mixing is 0 for ideal solution and it is not for non-ideal solution. Interaction between the components, that is A, B, AA, BB. These are all the interactions. Pure components have interaction AA, BB, and between the component means AB components. So this A and B interaction, suppose it is nearly equal to the AA, BB, then it shows nearly ideal behavior. We call it as ideal solution. Actually, there is no perfect ideal solution, but we call it as ideal solution. And when there is a large deviation or difference between the interaction AA, BB and AB, then we call it as a non-ideal solution. Now, in ideal solution, as we all know, each component obeys Raoult's law at all temperature and concentration. That means Pa is equal to Pa0 XA. And it is not equal to Pa0 XA for non-ideal system. This means in ideal no heat is evolved or absorbed, but non-ideal system deals with that also. Now this is the vapor pressure curve for the two component system. In this, dotted line represents the ideal system, but the curves are showing deviation from dotted line. This is positive deviation and in this there is a negative deviation. And at the molecular level, why this happens? This happens because the ideal behavior having AA-BB interaction nearly equal to AB interaction. But the solution which do not obey Raoult's law, they are called as non-ideal solution. It can be possible that the total vapor pressure is greater than the corresponding pressure. So they shows positive deviation. That means Pa is not equal to this, but Pa is slightly greater than this. Pb is also greater than this. So total pressure, it is always greater than this. Then delta H of mixing is also positive because energy is required to break the bond. Dissolution process, that's why endothermic. And there is a decrease in the magnitude of the intermolecular forces. Molecules are loosely held and that's why they are away from each other, increasing the volume. That means del V positive. Now, in case of negative deviation, exactly opposite is the situation. The attractive forces AA, BB, they are weaker than AB. That means molecule come closer. They are tightly held and that's why delta V will be negative, contracted, contraction, volume contraction. Also, this Pa and Pb will be less than Raoult's law and the total pressure will be always less than this. So, when we deal, there are different examples for this. Like ethyl alcohol, cyclohexane, acetone, carbon disulfide, benzene acetone, these are all the pairs showing positive deviation. Similarly, there are some pairs which shows negative deviation. So now acetone and aniline, acetone and chloroform, nitric acid and chloroform, all these pairs show negative deviation. So we have seen the differences between ideal and non-ideal solution. Some liquid on mixing form azeotrophs, which are binary mixtures having same composition in liquid and vapor phase and boil at a constant temperature. In such cases, it is not possible to separate the components by distillation process. There are two types of azeotrophs called as minimum boiling azeotroph and maximum boiling azeotrophs. We will discuss it later on. Now, we are going to study the non-ideal mixture of liquids. This is the vapor pressure composition curve. Vapor pressure composition curve. Because of the Raoult's law, if we plot the vapor pressure of ideal mixture, then against composition we will get a straight line. In this case, pure A has higher vapor pressure, so it is the more volatile. Raoult's law only works for ideal mixture. In this, the forces between the particle in the mixture, they are exactly the same as those in pure liquid. So tendency for the particle to escape is the same as the mixture and also as the pure liquid. So that's not the non-ideal mixture. So there can be the deviation which from the Raoult's law. We will see the positive deviation. In mixture, the positive deviation from Raoult's law, the vapor pressure is always higher than what you expect. Basically, there are three types of solution. The deviation can be small, in which straight line in the graph turns into slight curve. This was the straight line. But now as there is a deviation, now it is turned into this curve. This is slight positive deviation. For example is cyclohexane carbon tetrachloride. This is an example showing small positive deviation. The vapor pressure of the component are slightly greater than that expected from Raoult's law. We can notice that the highest vapor pressure anywhere is still within the vapor pressure of pure A. This is the vapor pressure of pure A and its vapor pressure lies below this vapor pressure. Below this vapor pressure of pure A. Whatever may be the vapor pressure, it will be below the vapor pressure of pure A. It will always remain within the vapor pressure where the deviation is small. It behaves just like ideal mixture. As far as the distillation process is concerned, such type of mixture behaves just like ideal. Now type 2. Some liquid mixture have very large deviation from Raoult's law and the curve becomes very much distorted curve. Such mixture over a range of composition have higher vapor pressure than that of pure liquid. See the vapor pressure of pure liquid. And it is in this limit, in this range. And the mixture is showing more vapor pressure than the vapor pressure of pure A. It is considerably greater than the expected. The total vapor pressure rises to maximum than any pure component. Whatever may be the vapor pressure of pure component, the mixture is showing maximum vapor pressure above that. The vapor pressure is no longer that of the pure liquid. So this fact also we have to consider while considering the distillation process. Now, why this deviation? The fact that vapor pressure is higher than the ideal in this mixture means that the molecules are breaking away more easily than they do in the pure liquid. That is because the intermolecular forces between A and B are less than whatever AB are less than AABB. You can see when you mix the liquid, less heat is evolved. When the new attraction are set up, then was absorbed to break the original one. Heat will therefore be absorbed when the liquid mix. The enthalpy change of mixing is endothermic. The example is ethanol and water. Having highly distorted curve. ethanol and water shows such type of behavior with maximum vapor pressure, and at that time composition is 95.6% ethanol. Now we will see third type. It is showing negative deviation from Raoult's law. In the exactly same way, you can have mixture with vapor pressure which are less than what would be expected than the Raoult's law. They show large negative deviation from ideal behavior, and vapor pressure of each component is considerably less than the predicted one. The total vapor pressure dips to minimum than either of the component. Example is acetone chloroform, water sulfuric acid, water nitric acid. If one component of binary mixture shows negative deviation, other must also show negative deviation. It is not possible that one is showing negative and another is showing positive. Such type of system is not possible. If one is showing positive, other will show positive. If one is showing negative, other will show negative. These are the cases where the molecule break away from the mixture less easily than pure liquid. New stronger forces must exist in the mixture than the original liquid. So you can easily observe that the heat is evolved. You can see then water sulfuric acid, water nitric acid mixture, heat is evolved when you mix it. More heat is given out. New stronger bonds are made, breaking the original ones. Now we will study the boiling point composition diagram. It is just like vapor pressure, just the liquid having more vapor pressure will have less boiling point, liquid having less vapor pressure will have high boiling point. The rest of the situation is same. Now you can see that temperature composition diagram. The lower line, it is the liquid line. This is the liquid line, as this is temperature. In the previous case, this is vapor, this is liquid. Sorry, this is liquid, this is vapor, but as this is temperature axis, so now this is liquid. As we increase the temperature, we go to pressure area, vapor area. So lower line, here this is the liquid section. Here gases, vapors. Means top line, it is a vapor line. Above this line, vapor phase exists, and below this line, liquid phase exists. The composition of any point between these lines can be given by a tie line. This line is known as tie line. Between the two curves, tie line. The point on the liquid curve of this line is used to determine the composition of the liquid at equilibrium with vapor above it. The point on the vapor curve shows the composition of the vapor phase. Suppose I want to see the composition of this. This will give me the composition of the vapor phase, and this will give me the composition of the liquid phase. However, it is not same as that simple. The vapor is richer in the more volatile component always. This intersects the upper curve and vapor pressure curve, and this intersect the lower curve, that is the liquid curve. So region between these two curves, it is a two-phase region. This is one phase, this is one phase, but the region between these two curves is a two-phase region. In this, liquid and gas, both the phases exist in equilibrium, and we can keep the track of that two phases. Above the upper curve, the sample has fully evaporated and the system is entirely gas. Below the curve, the system is entirely a liquid, and here two phases exist. This simply means that the mole fraction of the more volatile component in the vapor, that is Ya. Remember, we are using mole fraction Ya, Yb for vapor phase. Mole fraction of more volatile component in the vapor Ya, it is higher than Xa always. So this process or this phenomena we have to take into consideration while studying the distillation process. Now, in case of non-ideal solution, we will take the example. It might not be possible to separate A and B completely. We will see that in distillation. Here are the curves. These curves shows maximum boiling and a minimum boiling. These are the azeotropes. We will see that in the next lecture. But these are showing deviation from the Raoult's law. So whatever you are plotting for the vapor pressure, exactly the diagram for boiling will be opposite. Now, we can conclude that in ideal solution, all the solution obeys Raoult's law. When the solution is showing positive deviation and negative deviation, they do not obey Raoult's law. Delta H is 0 for ideal and delta H is greater than 0. Process is endothermic, heat is absorbed for positive deviation. Delta H is less than 0, exothermic, heat is evolved for negative deviation. Delta V of mixing is 0 for ideal solution. It is greater than 0 for positive deviation, less than 0 for negative deviation. So these are the main point of differences which you have to remember while studying this unit. Remaining part we will see in the next module.